Can I start?
Well, I think the pace of people joining has slowed down. So, yes, you can start. And thanks everybody for coming to today's virtual learning session.
Awesome. Well, hi, everybody. I'm Rick Donnelly. Um, I'm here to drag you through Machine Learning 101 today with my co-host Kyle Ward and Mausam Duggal. And it's almost impossible to convey all of this in 90 minutes, so I'm trying to give you the basics, kind of to whet your appetite rather than to equip you. And a lot of the fun stuff is going to be on Friday, where we're going to walk you through 3 case studies. But today, in order to get your mind in the same place that we are, it's mostly a lecture with all due apologies, although please jump in with questions. So the way to do that is to get into the chat box, and Kyle Ward is going to be surveilling that while I'm running the presentation. And I guess with that, we'll get on to it. One of my colleagues challenged me to get through this conversation without introducing and dragging you through Bayes' theorem. I'm going to do my best to do that, but we'll see how it works out. So Elizabeth wanted me to have a picture so you can see me, but really now that you've seen me, I'm going to turn my video off because I've been having some problems with bandwidth recently, and I'm just going to go give the presentation. So nice to see you all, and on with the show, as they say. Get moving here. So as I mentioned, today, a play in 5 acts. Talked a little bit about the big picture. Can't talk about ML without data. Then I'll finally get into kind of what's under the hood in ML, some issues in practice, and then we'll let Kyle answer any questions and correct everything I said in today. On Friday, we plan to talk about 3 different case studies that you see there on the right, and they're all transportation oriented and things that we've done. So therefore, hopefully will be a lot more interesting to you. So our cast of characters, you can see our mugshots up on the screen. I'll do most of the talking today with Kyle, like I said, providing all the answers and corrections. And I'll admit at the outset, I am not a machine learning pro, and I might not ever be. Mausam has forgotten more than I've ever learned about machine learning. And I actually got into machine learning on a bet, which I'm going to explain on Friday. But most of my immersion to date has not come from transport at all, but rather from helping some friends out in a field called computational psychiatry, which I'll talk a little bit along the way. So let's start out with kind of a high-level overview to create a little bit of context. Machine learning sits here in the middle, and we're going to get to some crisp definitions of it in a moment. But as a reminder, it's kind of fits into the bigger world of artificial intelligence, and there are some substrates of it, like deep learning with deep neural nets, that are really interesting that we'll talk a little bit about today. One of the great books out there to get your mind around AI and where it's at is Kai-Fu Lee's book on AI superpowers, and I've stolen a little bit from his presentation here to kind of put this in perspective. He talks about 4 waves of AI: internet AI, business AI, perception AI, and autonomous, and he says that we're kind of between the second and the third right now. And for most of the work we're doing, you really need 4 things: massive data, great algorithms, a narrow domain to apply this thing to, and a concrete goal. But really, that's in order to do the R&D on this thing. In order to make it practical, we need to get it out to a lot of people, and that's kind of the point on the right-hand side. I view this as kind of a duality, where there are some things that we humans are always going to do better than machines, and there are some things that machines we just are not going to be able to compete with. And in my mind, the most important place to be in is where you're harnessing both of those in order to do greater things than you could do either one of them individually. So the 4 ways of AI kind of correspond to the 3 waves of travel demand forecasting, or at least as I've liked to characterize them. And machine learning unquestionably has a big role to play with some of the data-driven models that are just now coming online. But they can also complement turn activity-based models in our second wave in some useful ways. So what is it? Well, everyone has their own favorite definition, and I've thrown a few up here to kind of whet your appetite. But I would make the point that there's some commonalities between these. One is that it's kind of autonomous, something done without humans. It's based on continuous data, not just a point in time, but more continual. And its value proposition is that it automates model building and doing predictions. And we're going to see some examples today of maybe how you can do that. But this will probably become more clear when we see it on Friday. Now, there is a perception out there that once you master machine learning, all you have to do is shovel in mass amounts of data into it to get a result. And that's not quite right. In fact, it's not even lucid. One of the pioneers in ML has put together this chart. Notice that the ML code, the little black box there in the middle, is how small it is. And I'm surrounded by much larger, more weighty tasks that we need to succeed at in order for machine learning to be anything more than just a simple set of computer programs. I'm going to focus mainly on the stuff kind of to the left, although some of the right-hand stuff you'll see examples of on Friday. So when we talk about machine learning, we talk about different types of learning, and I've listed on the screen a couple of examples from our domain. Supervised learning is by far the most common, and that just occurs when the training data contains the correct outcome. In other words, both predictors and a response variable. And we have CML, classical machine learning, and deep learning models of auto ownership and mode choice have been attempted by a lot of academics, as well as by the 3 stooges here. There's also reinforcement learning, which occurs when the training does not include a unique correct outcome, but rather a measure of how good or what kind of utility you get out of the coded outcome. And this is especially good for learning games. And so you see a lot in enforcement learning when you see people playing Go with machine learning and things like that. Then there's unsupervised learning, which, as its name implies, contains no outcome information at all. So you feed it the raw data, and the machine looks for patterns or clusters in the data, as well as structure, and gives it back to you. And finally, generative learning creates new ideas or insights into behavior based on experiments and exploration. So the idea here is that we're constantly updating our priors, think, Bayes' theorem, based on new experience, knowledge, and what we observe about interactions. Now, you might hear about semi-supervised learning, which is a bit slippery to define. Probably the easiest way I can explain this is imagine having a data set from a travel survey where half of the observations have the mode of travel coded and the other half do not. And you're trying to use these data to look at mode choice. So there are methods within the machine learning realm that would allow you to approach something like that. There are a blizzard of methods out there in machine learning. And I haven't run across anyone yet that knows all of these. In fact, I'm not sure I know anyone that can define half of these, much less use them. So usually you look at a domain and you start looking at things within it in order to deepen your knowledge. Like some of the techniques that are used in medicine are a lot different than the kind of techniques that I will be showing you here today. When I think of machine learning, I think of a diagram like this because this more operationalizes it. I start with a use case, a problem to solve. I pull together the data. I train my machine learning model, which generates a prediction machine, and then I evaluate, I predict with it. And using it, I develop knowledge and insight just like I do with a traditional travel model. Notice that I have both training and testing data that I use, and we make a big deal about how much we use that in all of these machine learning trials. So the thing to notice about this diagram is that the most important thing coming out of this thing is the generative knowledge loop across the top, thinking about how you think about your problems and strategies. And the 80-20 rule definitely applies here. You will spend at least 80% of your effort just preparing the data. We'll talk about this later when we review some of the limitations. And the other thing about machine learning that you should know is that the prediction machine truly is a black box. It's a binary file that's created by the machine learning system, and it is totally undecipherable by humans. There's one important exception that we're going to see later called decision trees that you can easily visualize. So the case for ML in my mind rests on what it can do and what it doesn't do. The value proposition revolves around its ability to highly automate those three boxes in the middle: data prep to prediction machine, and learn patterns that are invisible to human analysts. And moreover, it really rigorously applies statistical and mathematical reasoning in ways that we humans just can't keep up with. But to re-emphasize from earlier, this is about where all of the effort goes into when you're building one of these machines. Now, one of the things it doesn't do is fall victim to a lot of the things that we humans do. And I'm not saying that we in transport planning are particularly victims to this, but we all have biases and prejudices that kind of shape how we view travel demand, transportation system, and how people respond to things and value them. Most of the people we prepare forecasts for have agendas, and no small amount of us have a genetic predisposition towards replication, especially of traffic counts in our models. That doesn't count the mistakes, either in conducting the analysis or interpreting the results. And something Howard Slavin put me onto is an excellent book by Kahneman, who talks about how we humans really struggle to deal with multiple dimensions of data in our mind, especially visualizing some of the interactions. And it turns out that the machine is really great at that. So in my mind, there are a lot of good reasons to consider ML, if nothing else, to satisfy my curiosity to what I can push it to that I can't do myself. Kyle, I presume there are no questions that have come in yet?
Well, so David actually mentioned, that black box isn't entirely true, and he says to check out explainable AI. And while I've not Googled that term yet, I'm assuming what he's talking about is how you can change inputs and kind of work with the black box to better understand it. But if you wanted to talk to that a little bit, that'd be good.
I think the black box nature of this thing will become clear when I talk about neural networks. So I will do so then. Yeah, there are ways that you can deduce what the model is doing inside by regularizing inputs and comparing outputs. But there's no way to get a look at the model it has constructed other than what you tell it to do. But I'll make it a point to talk about that as we go on. Anything else?
That's it.
Cool. On the data side, I'll talk a lot today about N versus P, or the number of observations versus the number of variables in our data. And this is just a picture here of something you're all familiar with, which is the person table out of a travel survey or a synthetic population. And we typically deal with cases where N is much larger than P, where we have many more observations than we do predictors. However, when you get a lot more observations than you do have predictors, you run into some statistical problems that I'm going to talk about a little bit later when I talk about high dimensionality. But we're used to seeing this. It may be hard to believe, but there are cases where N is a lot less than P. So in computational psychiatry, for example, I'm dealing with a data set now where we have about 1,200 variables, and we're on our way to about 5,000 features for every patient. Right now we have 892 patients in this particular database, which yields about 6,000 clinical outcomes. So because I have so many more predictors or features than I do observations, I can't use regression of any kind. And those are just classification variables. I haven't even converted them into dummy variables yet. So this is where machine learning really takes on, but admittedly not something that we see. Most of us are going to be using data from one or two sources. One is travel surveys, and the other is passive cellular tracking data. So Mausam's going to talk a lot about that on Friday, and Kyle and I are going to mainly focus on the traditional travel survey stuff. And most of us don't have a survey large enough to really do machine learning justice or to really exercise a lot of its potential. But if we start combining travel surveys in different sort of ways, we can eventually build up to a set of databases that will probably enable us to do many great things. The other thing that you're going to have to deal with in machine learning that we've talked a lot about in conferences at TRB and other places recently, but that's really coming to grips with big data and what it is. Because if you're acquiring big data from a provider, you need to know something about it. So in this diagram here, I've just made a couple of circles, and the dimensions are age versus income. Ideally, if I wanted to sample 50% of the population, I would go in all of those directions evenly, so I wasn't biasing my sample in any way. When we do a household travel survey, we typically get older people, and we typically struggle to get upper income people into our sample. But if you look at the total population, you can see the circles there that represent how big of a snapshot of the population that you can obtain. So a typical travel survey might get 1% of the population. The largest travel survey I've seen to date is the Transportation Tomorrow survey in Ontario, Canada. But still, pretty small picture. If you look at AirSage and Android, and you think about the people that typically were the first adopters and the most prolific users of them, they're not quite an unbiased sample, but it's pretty doggone large. And the fourth slice is one that we turn to most often because we don't have access to some of the location services data ourselves. We looked at third-party location service providers and aggregators, and they do sell big data, but I don't know how big it is, and I don't know the extent of its coverage. And my point here is that if you have a petabyte of data from a small subset of the population, that is definitely big data. But if you have a terabyte of data that is a very large sample of the population for a smaller instance of time, like in panel A here, you also have big data that is arguably better, and you need to know which of the two you're getting. So it's important that when you're focusing on these data, that transparency in source and methods, you don't necessarily need to see who the data applies to, but you need to at least understand where it comes from and how it was collected and in order to understand the biases you're going to see when you crank up your machine learner. And you need to know something about the confidence intervals in your data. And without that, you're going to really struggle to do great things with machine learning. The other thing I'd like to tell you about is something called cross-validation of our data, because in an ideal world, we would have a large data set that we train our models with and an equally large data set that we test it against. In practice, we never have that luxury. And so we turn to cross-validation in order to train and to calibrate our ML models. So in a simple case in panel A there, we might just take some proportion of our training data and just set it aside and use it to test our model. But in cross-validation, there are two primary methods that we're going to use. One is a single observation held out, where we take our training data and we take out one observation and we use that one observation to validate the model we train with. And then we repeat that for every unique observation in our training data set. Likewise, in k-fold cross-validation, we do our validation in chunks. And here you see that I might build a model with 90% of my data, holding out 10%, and I'll build it again with another chunk, and so on until I've looked at all of the chunks. And in machine learning, we typically simply come up with a composite score of the mean square error or some sort of a classification error measure for each of those when we do cross classification. And there are more advanced methods going along, but I'll stop here and ask Kyle if we have any questions.
Yeah, we do. We had one question that was, what would you think is large enough for a household survey? And I would just add on to that. It probably depends on what you're going to do with it. But so maybe you could say,
absolutely,
mode choice versus, something simpler.
I can only tell you anecdotally that when trying some of these machine learning models out with Toronto, where I have a household survey of 5% of the households in the population collected every 5 years. So if I combine 2 years together, I have, and you assume that there's no overlap, I have roughly 10% of the population versus a typical household travel survey of about 1/2 to 1% of the population. The error in the models, if I apply the same model and build up the training data the exact same way, I typically see a much greater accuracy, predictive accuracy out of the models built with Toronto data than I do with individual smaller samples. Maybe a function of how I'm doing it and how I'm building it up, but that's what I think I've found. What do you think, Kyle?
I think you've covered it.
Anything else?
So yeah, Elizabeth also asked, she's curious if there have been studies about differences in estimation of, logistical regression when using k-folds. So in other words, k-fold is a really big feature of ML, but have people used it? Have they tried to incorporate it for log regression models? And Elizabeth, sorry if I butchered your question.
Yes, absolutely. I'll get to logistic regression in just a moment, but it is very common that we'll go through and we'll use cross-validation to build up a model, and the average of 10 builds of that model where I'm holding out 10% each, and I average the results, I get much better outcomes than I do just using any single one of them. Now you could try to choose the antithetical. In other words, run it 10 times and see which one comes closest to the mean and just take that linear log regression model. And I guess if you're going to just build a model once, that's great. But one of the great things about machine learning is that it continually can update models and continually do this in order to keep improving the model. I'm going to show you an example of how cross-validation improves the estimates from some example data I have. So we'll look at that in a moment. What else, Kyle?
That's it.
Okay, so let's look at what's under the hood in machine learning. And what's under the hood are all those methods I showed you on that very busy diagram earlier. But let's start with really simple stuff and move forward. There are two qualities of a model, whether you're building a classical model or a machine learning model, that you need to keep in mind, and they're unhelpfully named the same as other concepts that we use and attach a different meaning to these words. One is variance and the other is bias. So some of the machine learning approaches are highly flexible. Linear regression is an example of something that's not flexible in that it only does one thing. Neural networks are very flexible, as are some of the boosting and bagging methods we'll see later. So the two terms that we focus on the most, one is variance, which is the amount of change in our model if we trained it using a different data set. In general, more flexible models have higher variances. In other words, they change more when you change the training data. Bias is the error introduced by representing a complicated system with a simple model. And we know that very few systems in the real world operate in a true linear relationship. But man, it is really a tractable and useful approximation, especially when you're first starting out. In general, of course, more flexible statistical methods have lower bias. So our goal is to select a model that has both low variance and low bias, which is kind of challenging. One of the problems we run into with machine learning, which you can also run into with statistics, but is that the more complexity you add to a model, the greater the likelihood you're going to overfit the training data at the expense of predictive accuracy. And so we see this graph that you see up here on the screen a lot, and we're going to come back to this as we move further on through our presentation. But for now, it's worth noting that if you look at this graph on the left, these are three examples of fitting some data in a textbook, a very good textbook actually, where you look at the mean squared error of this particular model, and you notice how variance in orange and the bias in blue work opposite to one another. And so our goal is always to choose a place where we minimize the predictive, not the training, but the predictive mean squared error. The problem is we don't know that. And so we have to use cross-validation, or there's some ways that we can enhance some of our models through mathematics to approximate this prediction MSE in order to come up with robust models. So I'd like to show you a brief example of some data from a stated preference survey that I pulled together to make some of these examples concrete. So I've got 120 observations in this data set, and you can see the structure there on the right. It's got three variables. One is the parking cost per hour at the destination end. The second variable is the ratio of transit travel time to auto travel time. And the third is the chosen choice. Now, these are commuters into a central city area. And in order to do logistic regression later on, I have to code the response variable that you see in the rightmost column as a binary variable to represent whether you're in auto or transit. But if you look at the dots on a screen, you can see that there is no great linear relationship there. And if I was going to do that, I might look at a simple linear model. And you're all familiar with the slope-intercept form, which is easily extended to multiple linear regression. And I again make the point, because it's going to be so central to everything you do in machine learning, that the error function, the expected error, is a function of these three variables: the variance, the bias, and the variance of your error term. And so we pay close attention to that when we build our models. And when we build models in machine learning, we use a lot of the same sort of error measures that you typically see elsewhere. We use the mean standard squared error in most cases, which is very similar to RMSE that I think probably most of you are familiar with. So I'm not going to belabor this, but we're just taking a look at the predicted versus the observed error and coming up with an error message that we can use that will guide some of our calculations. So, not surprisingly, if I do a linear regression on my data, I get not a great fit. I don't know if you can see my little cursor on the screen, but it's an adjusted R-square of 0.44. But more importantly, if I look at the plot of the residuals on the right, I see that it is not randomly distributed, which is great insight into the limitation of linear regression. But I can turn to logistic regression, and it's very similar, although not as familiar to a lot of people in transport planning. But it also has a slope-intercept form, just like a regular linear model, except that we're looking for probabilities instead of exact outcomes. And with a little bit of logit, rearranging this thing on the bottom, you see something that should look really familiar, the log odds, or the logit formulation of our model. And we can extend this into a multiple variable logistic regression very easily, following the same sort of math. When I do that, on this particular model, it's stunningly simple. All I'm doing is I'm running a model where I the transit auto ratio, and I tell it I want to build a binomial model, which is a logistic regression. And it goes through and I translate those probabilities that come out into either auto or transit, and I come up with a confusion matrix, which I'll talk about in a moment, and I find that the accuracy is 0.56. So I'm already doing better than my linear model, and the screen that you see there on the right, or the lower right, shows you what happens when I do logistic regression on these data with both variables. In other words, two predictors. My accuracy jumps up to 0.83. So at this point, I would feel pretty happy. And if I were running a traditional model, I might conclude I'm at a great stopping point, but there's still a lot more I can do with this. One thing I want to get clear in everyone's mind before we go there, though, is this whole idea of a confusion matrix, which is unhelpfully named because it's not confusing at all. It's simply a truth table. So you see that this is a different data set, but I have observed modes on the rows and I have simulated modes on the column. And the accuracy is simply the sum of the diagonal, which is where my observed and my simulated are exactly equal, versus divided by the sum of the matrix, where everything that's not is, of course, a classification error. By convention, when we write reports and put the stuff in journal, we usually put the observed on the rows and the simulated on the columns. But of course, if you look at this and think about it a minute, it doesn't matter which way you put it on. The one limitation of using regression models, and we in transport are worse at this than almost any other profession I see, is that there are a lot of things that can go wrong with these models when you get into doing multivariate regression. And yet, we so rarely look at any of this stuff. And I struggle to find reports or presentations that some of our colleagues have done where they've gone through and they've looked at a lot of these things. Outliers are one of my favorites, and multicollinearity and logit model utility expressions just don't get me started on that. But let's just look at one of these things, overfitting, and try to understand what happens when we do that. And the reason I go into this is because this is a big problem in machine learning. And moreover, I hasten to point out, all of these issues with the regression model, things that we don't normally test for, but should if we were really rigorous, are in addition to all the human errors that we might make in constructing and interpreting our models. So overfitting is real easy. My definition is there in the middle, although I guess that's more symptoms than a real good definition. Or I have a small training error and a large test error. In other words, the two error functions have started to diverge. And you see some graphical examples down there below. And if you're into machine learning, you are constantly testing and worried, almost to the point of obsession, about overfitting your data, because there are some models that we deal with that are just excellent at doing that. So we care about this because you can greatly fit your data and have zero predictive accuracy. And this is especially problematic with high dimensional data where you have a lot more observations than you have features or predictors, which is exactly the case that we have in household travel surveys and in synthetic populations. So there are a variety of ways that we can mitigate this. One thing that I do is we map it out, we make a graphic of it very often so that at every particular point along the way, we know where we're at with respect to finding this optimal stopping point where we've reduced our predictive error to the maximum possible. There are some other ways that we can do this, though, that are more formal and less visual. There's a process called regularization that I'll talk about in a little bit when we get to neural nets. But we have shrinkage methods to remove features that aren't terribly helpful. We can stop early, and we cross-validate, and cross-validate these models. That said, this fitting problem is everywhere in machine learning, whereas the regression problems I showed you just a moment ago, they probably pretty much stay with regression. So here's another way that when we start looking at classification methods in ML, that we can start looking at our data. So these are the same data I showed you just a little while ago, and they're broken into regions by a process called k-nearest neighbors. And it very simply takes every point within my response surface here, and I average it with the closest k number of neighbors to come up with a response surface that you see there demarcated, in my case, simply between two regions because I have two predictors. And I can choose the number of adjacent nodes or neighbors that I can include in my calculation. And counterintuitively, the more I include, the better I do not get. When I jump from 3 in the leftmost panel to 8 in the center, I actually get a fragmented boundary. And it's not until I get up to 13, which generalizes a bit too much, that I'm able to come back and look at it and say, actually, the simpler model, the one with the less bias, number 3, is the most accurate. Now, I'll admit that this is kind of based on my very simple example. And if you had more features or more data, you might see something different. But this is a pattern that you typically see, that unless you have very highly dimensional data, simpler models just work better. The nice thing about this is that this is really easy to put together. So you saw my data earlier, and all I'm doing here is I have a line ran where I'm sampling, and I'm saying I want 90% of my data to be in the training data and 10% not. And so you see my listing of ran there. And then I'm just going to partition my data into a training database, df_train, or df_test, depending on whether or not they happen to be in those random draws. And then I just run my KNN model. I run the training data, I compare it to the test data, and I'm using 3 folds. So in other words, the one I saw there on the left, and it changes every time because every time I run this thing, I get a different 90% of the data in my sample. But in this particular run through, it gives me 100% accuracy. You can see in my matrix there. So I'm pretty happy about that. And this is a lot more accurate, obviously, than anything I can achieve with linear regression. So where are we so far? Here are some results of models. The first line, linear regression, remember, when I applied this model to my data, I got a predictive accuracy of 0.32. Notice that the predictive accuracy is different than the adjusted R-squared, which is a little bit more generous. The same thing happens, it turns out, when you're looking at logit models, when you're trying to evaluate the accuracy of a logit model using a Rhodes square statistic. It moves in the same general direction, but it is not the same thing as predictive accuracy. One of the nice things about working in multi-agent models like we do in activity-based models is that you can go through and you can build these confusion matrices very easily and unambiguously, whereas we of course cannot do this with our aggregate models. But in my case, my regression looks pretty awful. The second line you see there's random guessing. So Kyle, put me to the task. He said, well, you can just guess randomly and do better than your linear regression. And he's right. And about half the time, I can randomly guess the mode, but I only get it right about half the time. And the graph you see there in the lower right-hand corner is the graph of, I don't know how many trials I did. I guess 100 trials where I just guessed at them. And you can see the distribution as well as the mean there. My logistic regression on one variable, the transit auto ratio, is 0.56. The multinomial logit, 0.8, very respectable. That model I have not shown you. That's a regular logit model, just fitted to this data using a logit. And it outperforms everything else so far, which is curious until you realize that the one above it only has one variable. When you look at the multivariate logistic regression, the 0.83, I ought to be very similar to the logit model because the underlying math is so similar. Finally, the last 3 rows you see there are the k nearest neighbor analyses, which meet or beat anything else that we've used so far. I'll stop here and ask if there are any questions. Kyle, hit me.
So we only had one question. We might have resolved it in the chat, but there
Cool.
was a question about whether, if negative values for your auto transit ratio, but I didn't actually see any. So I think maybe we'll skip it. And then Elizabeth says, KNN requires maintenance of data. She just brings it up as good to note. So it's a good point.
Agreed. I'll have to go back and look. I don't know why why would it be negative? Because it should be from 0 to infinity.
Yeah, it may have just been
I haven't looked at those data in a long time. I just pulled them in to use them in this. So I will go back and look. Thank you for noticing that. I'd like to go on now and talk about decision trees because they are a big part of the ML landscape. And here's my data again. And we can use tree-based methods for both classification and regression problems. And the goal is to map the decision space into a number of rectangular regions like you see here. And we typically use the mean within each of these regions for the prediction for regression models and the most commonly occurring factor in each for classification data. And so our goal is to find boxes that minimize the RSS for regression or some surrogate of classification error, such as a Gini coefficient, that is better for growing trees. And so we use a process called recursive binary splitting to divide the entire region into 2 regions that result in the greatest reduction in RSS. And that's the vertical line you see there. And then we recursively split each of the 2 regions created using the same process and so on until we reach some user-defined stopping criteria. Now, with only 2 predictors, I don't have to go very far in order to stop. I have a very simple tree, and it's very simple to visualize, which is why I like these data. This approach has a tendency to overfit the data, so we often will grow a large tree, which I'll show you in a minute, and we prune it back successively until we find a solution that's called a subtree that trades off variance and fit. And there are a lot of different pruning algorithms out there, not worth going into today. Trees are better than linear regression or any of its extensions when the predictors are nonlinear, as in the case of my SP survey example. And because the results are highly visual, they're easy to explain to people. So let's look a little bit closer at what's under the hood here. I build a tree really easily by doing repetitive partitioning. And I have a model statement there at the top of my screen that looks very much like fitting a linear model. And you can see when I print this thing out, the tree that it creates. So there's a trunk, which is the root, and I have branches. And finally, at the very end, I have leaves, which are kind of illustrated this way. So in this case, when I built this tree, it said, well, if the parking cost per hour is less than $1.90, you're going to take auto. But if it's greater than or equal to $1.90, you're more likely to take transit. But let's break that down further and say, well, if that transit to auto ratio is greater than 2.4, I'm going to take transit. And if it's less than that, I'll probably drive. And you saw that in the decision space earlier. Now, the problem with this, to the extent that you might say that it is a problem, is that if I run this again, I'll get a different outcome. And you can see here that in the 2 trees I've built, that the leaves or the end prediction at the bottom are different. And so we have different ways of resolving this problem. You could just run it a bunch and aggregate it, which is something that we do often. So we have a category of approaches we call ensemble approaches to take decision trees one step further. Because the trees themselves are not very useful for that for the property I just showed you. And in addition, even when they work fine, they typically don't do as well as other supervised learning techniques. But you can juice them up using bagging, boosting, or random forests, and in so doing, you typically obtain large improvements in your accuracy. So when we're using these enhancements, we're using multiple trees that we combine in a variety of ways to yield a single composite prediction. And there are 3 ways we do this with a lot of variance on each. So the top one you see here is called bootstrap aggregation, or bagging for short. And the goal here is to generate a large number of trees from different subsets of the training data and then average the resulting predictions. You get substantial improvements in predictive accuracy when you use a couple of hundred to a few thousand trees to do this averaging with. And so that's what you see there on the top going on with bagging. Typically when you do bagging, you will give it all of your training data, and it will take different slices of the data to build these individual trees with. And it usually uses 2/3 of the data for training and the other third for what's called out-of-bag samples, or what it validates against. Boosting is a bit harder to explain, at least without getting into math. It does not use the bootstrapping, the repeatedly drawing same random subsets of the training data, but rather it incrementally improves on previous iterations of the original tree. And in one case, it'll fit the tree to the residuals of the model rather than the predictors. And so both of these use kind of a variant of voting to come up with its final prediction, and it combines trees. But in bagging, we give equal weight to each of these different trees, whereas in boosting, each model's weights are influenced and contributed by its predecessor. And we call boosting slow learning because it goes through many different cycles, making small changes in the residuals in order to come up with a great solution. There is something out there that is all the rage in machine learning called extreme gradient boosting, or XGBoost, that's very fast and powerful improvement over this bagging that you see, or simple boosting that you see here on the bottom. And it's complicated enough, we could probably spend an entire workshop on it alone. But Mausam is going to try to make it humanly understandable when we talk later on Friday about this. So in bagging, I'm going to further take my data and I'm going to run it through bagging. And what you see here is that I'm going to go through and I'm going to build a bunch of bagging experiments, and I'm going to vary from 10 to 200 the number of trees that it will build in each run of the bagging. And I'm going to save the RMSE results from it, and I hope to see a decline in error as the bagging proceeds. And indeed, I do. Because of the stochastic nature, you don't get a smooth gradient descent like you would expect to. And in these particular data, because it's so small and only has 2 features, it's hard to see a great reduction in RMSE, but it's decent. And the more features that you have in the model, generally, the bigger the reduction that bagging is going to give you. Although there are a lot of exceptions, obviously, in a lot of cases. There's also a generalization of bagging called random forest. And the goal here is to decorrelate the trees. Now, when we do a regular bagging, the trees are all correlated because they come from the same data. And in this case, instead of building nearly identical trees, varying only the observations used, we only sample a subset of the features or of the predictor values. We typically take the square root of all of them, which in this case would be 1. So building a random forest for my trivial data set is not terribly informative, but when you have a lot of predictors, like in my computational psychiatry example, you can see some remarkable improvements in the model. So when it goes through and it will choose a feature, one feature from that small subset, the square root of all of them, and it'll build a random forest tree. And then at the very end, it takes the same kind of voting of outcomes on my data. In a machine learner, like all of the examples I've shown you before, this just comes out as a binary data stack. And you run this thing through with any kind of data, and it will apply the tree that you've trained and hopefully cross-validate it. So if I go through and I look at this, if I just do a decision tree, I get a predictive error or predictive accuracy of 0.89. And if I go through and I do bagging, which I showed you earlier, it cranks it up to a predictive accuracy of 0.96. I have not checked that I'm not overfitting the data, and with such a small data set, obviously I'm probably pulling a lot of repetitive samples that are either the same or close together. So I wouldn't expect to see this big a range over a larger data set or with more features, but I would expect to see it move in this direction. And the cool thing about this is that you can do this, as you've seen, with just a few lines of code. And so it works pretty decently. Kyle, maybe I'll stop here. Do you want to add anything or
so
throw
there's
any
actually,
questions?
there's been a really good discussion in the chat, but I think we've got all the questions and extra explanation provided. So I think
We'll summarize it.
So there was questions about, so like in a mode choice model, part of the bias that we put in is which questions to ask first, right? So we put like major mode at the top, and maybe you might, well, where exactly does access mode go? Is it third level or fourth or something? And so the question was, do decision trees have that same issue? And for anyone not following the chat, decision trees actually determine which questions to ask first. You don't tell them, and they do it based on trying to maximize information gain or the Guinea index or a couple other different things. But it's basically a measure back when Rick showed kind of his two partitions of the data, which one kind of maximizes the differences between the two groups. And then, I think that's pretty much it for now. Some questions on what we're going to cover later, but the answer luckily was yes to all of them. So we're good.
Well, you don't know what I'm going to cover later, so that's maybe presumptuous. But what I would like to do is I'd like to turn to neural nets now, because there's probably nothing more hyped and mysterious about machine learning than neural nets. But there's also probably nothing with less potential or more potential than neural nets for certain types of problems. Under the hood, they're just nonlinear statistical models, or maybe a better way to put it is that they're two-stage nonlinear models, and they can handle either regression or classification problems. So what I've shown you here on the screen is a schematic of a neural network for regression. So the same inputs that we put in our traditional regression models are on the bottom row, the input layer there, and we get a single response out at the top, just like we do in a regular regression model. Well, what's in the middle is called a hidden layer, and there are almost always more than one row of units within it. In fact, they're usually between 5 and 100 hidden units, and there are a lot of factors that go into tuning the numbers, and a lot of it has to do with some of your training data and what you're trying to get out of this thing. We'll talk about more about that in a minute. So these derived units, or these hidden nodes, are created from linear combinations of the inputs, as you can easily see. And the target, or our prediction Y, is just modeled as a function of linear combinations of these things. So it successively combines all of the data. And the hidden nodes are activated by a sigmoidal rather than a binomial function that we see in a logistic regression model. And I've shown that there to the right. And sometimes Gaussian features are used as well, but that's beyond what I think I know about neural nets. So as you can see, we're successively combining as we go up this net. If I look at a more general form, we can also use neural nets for classification where we're interested in probabilities instead of distinct deterministic outcomes. So we have to have more units in the output layer. In fact, we have one for every labeled outcome. So if we're doing a classification model, we'll produce probabilities that'll sum to unity. You also notice on the right-hand side that I've included what are called bias units feeding into each hidden and output layer. You may hear about these things, but they simply capture the intercepts in the derived, in the equations in the hidden nodes and in the error functions. I guess early approaches to these things, when I first started looking at them, they use standard linear functions or something similar to a logit model for each one of these nodes in the hidden layer. And the parameters of each of the functions within each of these little nodes are learned from the data. But it's perhaps more accurate to look at these as each one of these are a linear logistic regression model, like we saw earlier. And their parameters are tuned using, from the training data, using maximum likelihood estimation. Because of the flexible nature of this thing, you can use it for either regression or classification. A lot of experts will say that this is a nonlinear generalization of linear models, regardless of which domain we're using them in. And the last thing I'd say about this that you need to know is that these links that you see in between the nodes in the hidden layer are called weights, and the goal is to fit values to them that best fit the training data. And to do that, of course, we need an error function that we're seeking to minimize. And you see on the upper left hand, there's something called R theta. And don't get tripped up in it, because if you look closely, it looks just like MSE, where we're looking at a simulated versus an observed outcome but we're looking at it from a number of functions, not just a single function. And we have something very similar for classification models right below it. And you notice on the end something new, a penalty term that prevents us from overfitting the training data, because neural networks go to overfitting like a thirsty horse going to a barn. And so a lot of the art of building neural nets is to prevent that outcome. And you can either do it by just stopping it after it trains for a short period of time, or more formally by putting some of these weights on there that we use to slow down the model's expansion of these factors away from 0. We don't want to push our theta to its global minimum because that's the ultimate in overfitting it. And so we use this lambda times j theta here as what's called a decay weight. Lambda is usually greater than 0, but not by much. And the larger its value, the more it will shrink the weights back towards 0 as you cycle through this model. And you can use cross-validation to estimate the value of lambda, but I'm not going to go into that today. The general approach to this, and there are a lot of different types of neural nets, and I'm going to show you some of them in a minute, or at least their names, is that you want to minimize our theta through something called a gradient descent. In neural networks, we call it BAP propagation. And the underlying math is decently dense, but in essence, we're doing a cycle like you see there on the right-hand side. In the forward pass through our network, the weights are fixed and we calculate the predicted values. And then on the backward pass, we're updating our error calculations, which then goes to the gradient descent, and we update our weights and we move forward. And so it should more aptly be looked at like a circle, or we're continually looping through this thing until we hit some stopping criterion. Back propagation like this is very slow. And so if you were using, like I did when it first came out, something called TensorFlow to build these neural nets, your model could run for days. And the only reason you would know that it hasn't crashed, which TensorFlow did, was the size of its training database, binary file, would just continually grow over time. And then miraculously it'd be done. But the more efficient nets are a lot more complicated. And in view of time, I'm not going to really go into them. But there is some interesting things to know about how you train a neural network. One is that more often than not, we standardize the inputs with a mean of 0 and a standard deviation of 1. I don't know that you have to do that, but I've never seen it not done by people that know what they're doing. In other words, people other than me. And what I gather from that is that standardizing the inputs ensures that all the variables are treated equally when the constraints are applied and when you go through regularization. The second thing is you have to specify those starting weights in a hidden layer. And they're usually set to values near 0, which starts the model out more or less linear, and then it becomes progressively more nonlinear as the weights increase. But you can't jumpstart the process by setting the values too high, because otherwise then the training kind of stumbles. And if you pick 0, you wind up a case where the model doesn't move at all. There's no movement in the model. Even in a simple neural net, like I showed you earlier, just the sheer number of all those weights, those arcs, will steer the model towards overfitting without any intervention. And so that is why we work so hard to prevent it from moving in that direction. And we typically use cross-validation, yet again, to pinpoint where to stop the process. Because typically running it longer will just start to increase the prediction error again, just like it does with more classical models. The decay weights are something that you must either use with some amount of experimentation in order to optimize their results. You don't have to use decay weights, but if you're not, we would typically stop this thing before it gets very deep. In general, you want more hidden layers than too few. But like everything else in machine learning, it's kind of a compromise. The reason we don't want too few is because you might miss some of the nonlinear relationships in your training data. And too many layers just adds computational burden, but we can usually solve that through regularization. And as a consequence, we tend to err on the top side more than on the bottom side when we go through this.
Rick, could I add something to that last point?
Of course.
Too many hidden layers can also handcuff your back prop. So basically, you're working backwards from the error in your final guesses up through your neural network back to your inputs. And if you have a ton, like 100 hidden layers, by the time backprop gets to like the first 2 or 3 layers, it's making very, very small changes. And so it can really deaden the sensitivity, lengthen the training time. It can do things like cause dead nodes and stuff like that. So there's definitely a trade-off.
Yeah, agreed. There's a lot to know about this. When we implement these things, we often do not implement a single neural net. The R theta function that we saw a moment ago is non-convex, so it has a lot of local minima in it. Thus, the solution we obtain is sort of dependent on the starting weights. In other words, it's a chaotic system if you're into systems theory. Oh, and I guess I should note that by chaotic, I'm not referring to something that's in disarray where the wheels are about to fall off the system, but by using it in the system science sense where the outcomes are highly sensitive to small changes in the inputs. That's when you see these things in practice, we tend to average the predictions over several networks, as you see here. Or as an alternative that's more formal and arguably more rigorous, we just use bagging that I described earlier, which just averages the prediction from randomly perturbed versions of the training data. And then on the right-hand side, you can see there are all kinds of different types of nets out there, each with different advantages and different uses. I've only taken you through just simple back propagation. But usually when you construct these things, it is as simple as that line you see there at the top, where I'm going to run a prediction. It's going to start up a bunch of virtual machines somewhere out in Amazon space. I'm going to run through a bunch of these nets. I'm going to grab all the results back, and I'm going to average them. And for the end user, you really can boil it down to a single line of code like that. There's, of course, a lot of code before it that define what the net instances are. And like I said, you got to spend a lot of time looking at your data to get it right. But that's kind of it about neural networks. Kyle, any more questions that have rolled in?
Nope, we're all caught up.
Good. Well, we had some getting this thing done on time too. I'd like to talk about a couple of issues in practice. So one critic of machine learning, Peter Voss, if you Google my title line here or type in the URL down at the bottom that I've shortened for you, has argued, as have some people in our profession even, that machine learning can never cut the rigorous requirements we have for robust behavioral models in our profession. And so he came up with this list, and I don't necessarily disagree with any of them. All of this is true about neural networks, and you have to keep this in mind because listening to the voice of the critics is often as informative as listening to the advocates. Now, in our particular realm, I would argue that 10 through 12 don't really apply. I have seen some work where people are trying to build in spatial relationships, and we don't deal with natural language applications here that a lot of other ML does. And I would certainly agree that it's not well suited for high-level reasoning. Or I wouldn't use machine learning as a substitute for planning any more than I would say that travel models are a good substitute for transportation planning. But I think if you look at these things, the ones I've shaded, you could say that the same limitations or drawbacks are true about the models that we build when we build through estimation and calibration and validation some of our more complicated advanced travel models. So you're not necessarily moving towards a more limiting framework. It has both its advantages and disadvantages. So when I look at it, I say I am trying to always overcome my own prejudice against a black box by balancing these two set of limitations. The machine certainly has limitations. There are a lot of data limitations, the quality, the quantity, the stationarity, which I'm going to talk about, show you an example in just a moment, and accessibility of the data. Some of our biggest challenges with machine learning is not that the data are not there, but gaining access to them where they're locked up behind a lot of walls. It is definitely a stochastic system, so it does not explain, it's not deterministic. It can only tell us how or what, but not why. And interpretability, except for some of the tree methods, is a bit of a problem unless you do a lot of post hoc testing in order to try to deduce what the model is doing under the hood. There's a thing called p-hacking that I see a lot on the medical side in the computational psychiatry world especially. P-hacking is where you're looking through mountains of data until you find some statistically significant correlation that'll allow you to get your paper into a journal or something. But wait, turns out it's spurious, especially in models with high bias, and especially high bias and highly dimensional data. There's AI solutionism, the belief that machine learning can solve all of humanity's problems, pretty much along the same line as we believe that activity-based models will solve all of transportation modeling problems. And then there are a lot of ethical concerns. But I need to look at those limitations against our human limitations and try to figure out, where do I go next? The one thing that we have not cracked and that I can think of that is still on the frontier for us, and maybe still limit what we can do with machine learning, is understanding how behavior changes over time. So here are some data that David Levinson published from some surveys in the Minneapolis-St. Paul area. And he looked in the left-hand pane at single worker households and multiple worker households and how their incidence of telecommuting has changed over time. I desperately wish there were data for 2020 from his data set, and that has as much careful attention paid to the analysis as Dave did. But I created the one on the right-hand side called Contagion, and it is a admittedly non-random sample of everyone I know who's staying at home and how often. And I would guess that our current state is going to relax into something between the 2010 bars there and the 2020 bar that I've concocted, but we don't know what it is. We have yet to figure out how in machine learning to communicate to the machine how things are changing over time. There's no way to specify that a year, how many years ago, et cetera, are a special variable that, like we can in time series analyses. But of course, we have the same problem with our classical models. If you would have calibrated even the best activity-based model in 1990 with the 2 bars for that, and you were to build a forecast for 2040 or 2030, and you only change the inputs, the socioeconomic data and networks, you come out with the same bars in 2030 that you have in 1990, or the same percentages in your simulated population. So this is something that we have yet to figure out how to go. So I'll close off by extolling Davidson's diagram. This is something put together by my very good friend and mentor, Bill Davidson, where he says, in an ideal world, when we do travel forecasting, we would start out from first principles asking, what story do I want to tell? What policy analyses do I want to inform? What questions do I want to answer for decision makers? And that would tell me the type of forecast I would need in order to answer them, which in turn would decide what kind of model would be best suited for building those forecasts, which in turn would make a decision about the platform being the code and data that we use to implement our model. We in travel modeling, I think it is not hard to argue, have been really focused on two right-hand boxes to the exclusion of the two left-hand boxes for a long time. And while I think that there are many out there that believe that if I'm as competent and as creative as they are brilliant, I could take their model and I could apply it to almost any set of forecasting, which is not quite true in retrospect. But why I'm interested in machine learning is because it has an advantage. If we can automate building and updating some of our models and allow the machine to carry most of those right two boxes, and I have a lot more time to do forecasting, which is what my clients want me to do anyway, I can focus on the left two boxes. The machine can do much better than any of us can do in the right two boxes, and it would seem like a marriage made in heaven. We're a long ways from getting there, but the first step moves us on a hike up and down the Pacific Coast Trail. So that's everything I've got. I thought we'd have 15 minutes for discussion, but we don't. Here are some references of the most influential things that I've learned from. And some of them I've referred to in this presentation, so you can screen snap that if you want. But that's it. Any questions?
None in the
Comments?
chat.
Criticisms? Is anyone still online?
Yes, we do have people still online. Yeah.
Okay.
So I guess we'll give a few seconds for people to type any questions in the chat, or I guess just unmute and ask.
Yeah, I don't Zoom enough to know, but I presume you can put up your hand sort of thing, and Mario can unmute them.
And everybody can unmute themselves, I think. I think that's
Oh, cool.
Okay, I don't see any hands up or anything, so we might be done.
Well, that would be great.
Of course,
I'm
there's
all for that.
always opportunity on. Of course, Billy would have to, as soon as I say that, he types his question. So let's say Billy Charlton says, "I'm curious about bias in machine learning. There were several high-profile instances in popular culture a few years back. What are we supposed to do to combat it?"
Well, there's two types of bias. There's bias in the model, which I talked about. What I didn't talk about, what Billy might be interested in, is bias in the data that we feed this thing in order to train the data, because it is certainly possible to bake in bias into our data, intentionally or unwittingly. And it's one of the biggest ethical debates that we have going on right now. I haven't seen a lot of discussion in transport circles about this topic. Most of the time, we don't worry about bias in our data, but arguably should. But I don't know. It's a good question. Kyle, you have any great thoughts on this?
No, they're probably not great. But I mean, I think just being aware of it is obviously the first step. I did want to, David Ranke, let me see if I can scroll up and see it. He commented that His TRB committee, which is ABJ70/AED50, is publishing a primer on machine learning for transportation,
Cool.
and encourages people to check out the website, which is a great idea. People not watching the chat, Elizabeth Saul says to hopefully fill out a survey, and she gives a link to it. And then let's see, we got some more questions coming in. I think feature importance is usually used for finding significance. Does it introduce identical significance in the model? I can speak to that, or you can.
Go ahead. I'll go after you.
So in my example on Friday, where I'll be using XGBoost, you'll see the feature importance charts. One interesting thing about feature importance is that, even when you're using like a neural net, when you ask R or Python to tell you about feature importance, it just uses a decision tree learner to tell you about it because it's the same information gain. So when you're using a decision tree, the feature importance is just a byproduct, and you can see exactly what your model's doing. So that's one of the benefits of decision trees, is by using it, you can see what your model's pivoting off of. If I understand your question correctly, I don't think it introduces identical significance. I don't think it works that way, but I may not be getting what you're saying exactly. Rick, what do you want to add?
I'm not sure what that means either. But it's probably more a problem on my end than on the questioning end.
Agreed. Same here.
I've seen people that have talked about using standardization in the data and running a standardized data set through a lot of these ML things, and then running the raw predictors through, and then backspin bias. I remember the name, but I don't remember how it works. But apparently, you can use that to start looking at feature significance. And there's a lot of other techniques as well. I'm going to talk about one on Friday. You're going to talk about one, so maybe we'll look at it then.
Okay. So Dave Ori asks, can you
Dave Ori, he can't ask a question.
He says, can you talk a bit about which of the ML or econometric formulations you would pick for making mode choice predictions from your toy example?
From my toy example, well, I could not train a neural net on it because I have only 2 predictors, and that quickly collapses to a logistic regression. So I couldn't go from there. For my 2 models, I would probably use the bagging from a decision tree. And the reason, well, problem with bagging is not as easy to interpret as a simple single decision tree. The cool thing about it is I like its visual interpretation, and everyone can explain and understand where the variables were in there. It's as fast as anything that we would code up and run through a loaded model. But where Dave's probably going on this is just guessing. I would go through all of the models that I have selected. I would find the one that has the lowest prediction error, and I would go with it. Okay. Generally.
We had a question about support vector machines.
Also, I would also go towards a model that has lower bias and lower variance over one that has more. And I wouldn't know that without running the model, and looking, because there's more complex models obviously suffer more from it. But that would be a consideration as well, I guess.
Okay. We had a question about support vector machines. Obviously, we didn't cover those learners, but did you want to just talk briefly about it?
Not really.
Okay.
It's sort of like, well, I don't know, Kyle, can you explain in 2 minutes? Because for me, it's kind of like a 5-slide sort of thing.
No, I have not used support vectors machines probably in 4 years. So I'm a little rusty on them. So I wouldn't want to try to speak to it.
I think I
That's
understand it. I just
good
can't
news.
explain it in a Q&A without, I wonder if I have any slides that have an example on this. Let me look real quick. You're right, I did not put one. I did not discuss it because actually when I rehearsed this thing, it took me a lot longer than it did today, but when you're nervous, you talk fast and you blow right through it, right?
Yep.
What's the next question?
So we did have a question
looking for this.
about, and this one we probably should talk a little bit about. We didn't mention actually too much about deep learning. We put it in one of our slides, but a question about how does deep learning fit in? What is it? That kind of stuff. More layers on your neural network.
Yeah, I guess that's one way to put it. Deep learning moves you more into the unsupervised learning paradigm. And most techniques I see out there are better for unsupervised learning, where I'm still learning patterns. In most cases, we don't suffer from that, at least not with some of the data that we typically use to build models with. So I haven't really explored that space that much.
So I can talk a little bit about it, which, I mentioned one of the problems with adding more layers to, for example, a neural network, because your basic back propagation is going to fail at some point to make meaningful changes. But in the deep learning space, there are more advanced, gradient descent algorithms that don't have those same problems. You can also use, different, instead of sigmoid functions, you can use different neural nodes, and there are other treatments that you can do. So at least from a neural network standpoint, deep learning really gets at some advanced approaches to dealing with basically more computations, deeper trees. I would say it also introduces other layers, like convolutional layers, which are really big for image classification and things like that. So it's there's a wealth of information there that I encourage everyone to go take a look at.
Most of the deep learning techniques that I've looked at are extensions of neural nets, as you mentioned, and they require massive amounts of data. And if there's one thing that defines our profession, is the lack of massive amounts of data. And so as a consequence, I've sort of ignored it up until now, because I'm not interested, but I just haven't been in that space where I have the data to use some of the techniques. Mausam studied a little bit with GANs, and maybe we'll talk about that on Friday a little bit. Other than that, I haven't really been in that space, so can't talk about it.
Okay, let's see. I think that's all of our questions.
Good, do we have any time left? Oh no, we're past time. Okay, good. Kyle, do you have any closing comments?
No, thank you for presenting.
All right, bye everybody. Stay safe and sane.
Bye, guys.
I'm signing off.
Thanks all. We'll see you on Friday.